bounded by the function f of x equals the square root of x squared minus, absolute value of x squared minus 4, and the x-axis between x equals 0 and x equals 3. Have a 30-second strategy conversation. You ready to talk in a little bit?
Find that, and then just plug in 3 first, that, and then minus, and you can 0. The absolute value when you find the
All right, I have seen on most papers, most folks are saying, okay, you want me to find the area? I can find the area. The area is going to be the integral from 0 to 3 of the absolute value of x squared minus 4 dx. How many of you have that on your paper? Okay, good. That's good news. I get to say, great, you know what you're doing? First point awarded. However, there is a problem. There is a big problem here that no one seems to have actually recognized it as a problem. Those absolute value bars are going to cause a major problem. A lot of you all are treating this problem as though it was just parentheses. And I'm seeing on most papers 1/3 x cubed minus 4x, and then you're going to go and evaluate and do all the things. The absolute value bars change everything. We have, hold on David, we have absolutely no integration formulas that involve integrating the absolute value of a function. We have none. There are none. None at all. So this doesn't mean we ignore the absolute value bars and pretend that they're not there. We need clever thinking. Marvin.
Do we find the zeros to see what will be below the x-axis?
Okay, so it sounds like you're thinking about this guy over here, f of x equals the absolute value of x squared minus 4. Like, you're thinking about like the function, you're thinking about the graph? Okay, not a bad idea. Nora?
I was thinking either just like follow them through the whole process or just make what's inside positive.
Okay, because the absolute value bars are there to turn things positive. Absolute value means distance from 0. Okay? If the absolute value bars were not there, how many guys are pretty confident you know exactly what that graph looks like without the absolute value bars? 1 person, 2 people, 3 people? Okay, a whole lot of folks. Without the absolute value bars, what you have is a parabola. Nice and easy. And I bet a lot of you know exactly where the roots are just by looking. Where are the roots? Where are the roots? X squared minus 4. Where are the roots?
-2 and 2.
They have to be at -2 and +2. So here's the problem. I want you to find the area from 0 to 3. So here's where x equals 0 is, but here's where x equals 3 is. You've got some part of the graph that comes before the root and some part that comes after. Way back in pre-calc, Mr. Salhotra talked to you guys about what absolute value bars do to a function. There's a transformation. There's a specific thing that I'm looking for here. Those absolute value bars do something very specific to the graph. I've already heard they turn negatives positive, right? Absolute value bars turn negatives positive. What's going to happen to your graph is any part of the graph that was below the x-axis gets flipped. But the part that is already above the x-axis stays the way that it is. So the actual graph, I'm going to like graph in green here, would look more like that. You'd have the black piece over here stays the way it is because those y values are positive. In between the two roots, you get below the x-axis, those y values are negative. The absolute value turns them all positive. And so that's what the graph looks like. And if you have your calculator handy and you want to graph it on the calculator, feel free. This is exactly what the graph looks like. Is everybody kind of okay? Well, the definite integral is just saying go find area. Right? I need to find the area from 0 to 3. I need this area over here and that area over there. One of these two is easier than the other one. It looks like a triangle partly because I just graphed it badly. It's not actually a triangle, it's a parabola. It's curving. But think about the absolute value bars. Did having the absolute value bars change this part of the graph? All the y values were positive, so it kind of goes back to the point earlier of like, well, the absolute value turns negatives into positives. And what happens with positives? Nothing happens. They stay the same. So for this part of the graph, which is not a triangle, but I understand why you guys think it looks like a triangle, whether you refer to this as the absolute value of x squared minus 4, or you say, you know what, I don't need the absolute value bars, it's fine, because all your y values were positive here. So what I can do is I can say that from 2 to 3, don't write the absolute value bars, I don't need them. But from 0 to 2, our parabola dipped below the x-axis, right? And the absolute value bar flipped that graph up above the x-axis. It turned all your negatives into positives. There's another way to do that without using the absolute value bars. What are you thinking?
Can we just do it normally and just, if it's negative, we just say it's positive?
So you said do it normally, and then what?
And then I guess put a negative before the x.
Not just before the x, but in front of
Yeah.
the whole thing. Right? All the absolute value bars are doing on this part here is the parabola that was below the x-axis, I'm turning it all positives. So what I'm choosing to do is breaking this guy up and writing it as like a piecewise integral and saying integrate, change the integrand so it's the negative of x squared minus 4 from 0 to 2. Find the definite integral. This part over here, find the definite integral from 2 to 3 and just don't use the absolute value bars. Here I didn't need the absolute value bars. Over here I did. Here's what I want to have happen. If you are in these three groups over here, finish off the integration for the first definite integral. These three groups over here, this part. Okay? If there's anything that I just talked about that went over your head that wasn't comfortable, now would be a great time to ask those questions. Ron Bear.
So do you solve for the derivative first?
We're not doing anything with the derivative.
Okay. Because the d of x changes.
Okay, remember the dx is there to tell you what your variable of integration is. Right, we're saying like x is the variable, not t, not theta. So one half of the room is evaluating one of the definite integrals, the other half of the room is evaluating the other definite integral. And if there's any questions, and I definitely want you guys to simplify. So I think the value of this first integral is 16/3. And walking around, I saw a lot of folks have 16/3. And I think the value of the second integral is 7/3. How many of you guys agree with me on the 16/3? Like you actually, you went through it and it all worked. And how many of you guys agree with me on the 7/3? Okay, and the final answer? The final answer? The final answer, Jose? What would you do for the final answer? You're gonna what? You're gonna have to add them together. Obviously, you don't get to do this in the middle of a quiz or in the middle of the test. But I would strongly recommend maybe you put a little star next to this one and come back to it later, because I think this whole idea of like, how did we get rid of the absolute value bars? That is the hard part. That's the most important piece. This was just a little bit of skills practice. This should have been some skills practice. But the split is worth coming back to make sure you get this under control. Everybody okay? Alright, let's try another challenging problem. I want to see what you guys can do with this. We're going to skip past model problem number 2 for right now. I want to see what you guys can do with challenge question 2 on the back. I want you to go all the way through. I want a simplified answer. It's a word problem. I want units.
Number 2, right?
Challenge problem number 2. Let's. Feel free to get some help from a friend if you need it. Much. One more time. Thank you. When you think you've got the right setup, call me over. I want to give you a clean bill of health on the setup part.
Oh, you're right.
That's K.
So,
Yep. Careful, 1.75 is not 7/3.
So, like 1.75 pile.
7/4. But I don't agree with your setup. Oh wait, no, never mind, I take that back, I do.
But it's still negative 5 or
Keep going. So Jonathan, quick question for you. What does V of t tell you here?
The rate at which air is being taken in.
Another way to say that is, this is how fast air is coming into your lungs. And I want to know what's the total volume that comes into your lungs. If you've got a how fast function and you want a how much, the thing that you have to do, you have a how fast function. But the question is, how much? This has got to be the bells and whistles going off in the head and realize that this has to be a definite integral. So the right setup is going to be the definite integral from 0 to 2 v of t dt, and I know a whole lot of you guys had that right. So I need to find the definite integral from 0 to 2 of 1.75 sine pi t over 2. If you're making good progress, just keep going. I want to talk to the folks who maybe aren't 100% sure where to go from here. Where are those folks? I see Daisy, I see Jennifer, I see some friends. Okay, what could you do? Take anything from the folks that are struggling a little bit. Edgar, what could you do?
Can we like factor out or like take out the 1.75?
And why can you take out the 1.75?
It's a constant.
It's a constant. You can always factor out constants. So now I've got 1.75 times the definite integral from 0 to 2 of pi t over 2 dt. Okay. So now I need to find the definite integral of sine of stuff. Well, what's the definite integral of sine? Daisy?
Negative cosine?
This has to be negative cosine. Now I want to be careful because this angle is what's going to mess you up. Right? Pi t over 2, a better way to think of pi t over 2, Eunice, what's a better way to think about pi t over 2?
Pi over 2 times t.
This is the same thing as pi over 2 times t. So now it's just a matter of saying, oh, this is just like sine kx, right? And we know that that antiderivative has to be negative 1 over k cosine kx plus Charlie. So the antiderivative of sine pi over 2 times t is negative 1 over pi over 2 cosine pi over 2 t. I've still got that 1.75 in front. I want to be careful because that's multiplying this guy here. And I have to integrate from 0 to 2. For the folks that are going solo, how many guys have this negative 1 over pi over 2? Or a better way to write it? Safer way to write it? Negative 2 over pi, right? A little keep it, change it, flip it action. So negative 2 over pi. And now the last thing, plug in the 2, plug in the 0. Maybe you want to clean this up a little bit. Nora decided she doesn't like decimals and made 1.75. Let's pretend you wrote 7 over 4 and not 7 over 3. We'll keep that between the two of us. So I've got 7 over 4 times negative 2 over pi cosine pi over 2 times 2 minus 7 over 4 times negative 2 over pi cosine pi over 2 times 0. Pi over 2 times 2.
Oh, pi.
Careful, careful, careful. Pi over 2 times pi
Two over.
is 2 pi over 2, or even better, pi. Cosine of pi?
Negative 1.
Cosine of pi has to be negative 1. So now I've got negative 1 times negative 2 over pi. So 2 over pi. So I've got 7 over 4 times 2 over pi. We're almost there. Pi over 2 times 0. 0. Cosine of 0. Cosine of 0. Cosine of 0 is 1. Negative 2 over pi times 1 is negative 2 over pi. Times this negative 7 over 4 makes it a positive 7 over 4 times 2 over pi. So I can make it 14 over 4 pi, 14 over 4 pi, which is 28 over 4 pi. That's a great answer. A better answer. The one more likely to show up on the multiple choice instead of 28 over 4 pi. How about 7, not 7 pi? 7, the pi is still in the denominator. So this is 7 over pi, and if I really want to push, what are the units? What are those units? Have to be. They have to be liters. Either you know that because the problem said find the total volume in liters, check, hold on Nora, or, well yeah, I guess that's how you have to know it's liters. Nora, what's up?
Where'd you get 7 over 4?
7 over 4. When you told me you don't like 1.75, you made it 7 over 4?
Yeah, but then I simplified. I got negative 7 over 2 pi. Yeah.
That would work. And so over here you'd have 7 over 2 pi and another 7 over 2 pi, which is 14 over 2 pi, which is 7 over pi. All right, one more challenge problem. These are meant to be harder than anything you're gonna see on the unit test. I want you to go to model problem number 2. All of my folks that are interested in biology and biomedical engineering, problem number 2 on the front is just for you.
Oh, okay. That's how he got punched.
I mean, I'm gonna post the video, I'm gonna, if I have it ready for you at that point. I mean, if you're here, you can watch it.
What would that help you?
It smells good.
Velocity v of the flow of blood at a distance r from the central axis of an artery of radius r is given by that function there. Where k is the constant of proportionality, find the average rate of flow of blood along the radius of the artery. Yep. For my reading? Oh, it's beautiful. Thank you very much. So, what's going on in this problem? I'll take anything from anybody. What's going on? Ranbir, what's going on?
How fast?
Okay, we know that this guy here represents how fast. Okay? Good. What else? I'll think anything else. What's going on in this problem? Edgar. Abraham. Sorry.
It's like a rate of change.
You see it as a rate of change? Okay. What else is going on? Noemi, what else is going on?
The average rate tells you to do the integral and then put the b minus a integral.
Okay, because this is a rate and I'm asking for average rate, that means I'm going to do an integral from a place to a place, my function divided by b minus a. I have a feeling though, like the visual isn't clear. We're talking about blood going through an artery, right? Mm-hmm. What arteries look like?
Like a pipe.
They're tubes.
The pipe.
So imagine a tube or a pipe, clearly not drawn to scale. My arteries are not this big. And this is my artery. Okay? The velocity of the flow of blood at a distance r from the central axis. The central axis just means like right down the middle. There's your central axis. As the blood goes through, all like your little blood droplets here are going to be at different places along the artery. I'm not trying to make a sine function. They're just, imagine like the blood flowing through these pipes. Okay? You've got, what they're saying is that the little r is how far the drops are from the central axis. It's a measure of how far away you are. Everybody okay? So depending on how far away I am, I'm going to move through at different rates. I might move faster, I might move slower, but it's all a function of how far I am from this central axis. They're asking for the average rate, so I am going to do an integral from a place to a place of my k big R squared minus little r squared. But I need to figure out what are my limits of integration.
0 at r.
Right, if little r is how far away I am from the central axis, what are my options? I could be right on the central axis, in which case the distance is 0, and the greatest I could be away from the central axis is the big R, right? I'm not going to be out here. We hopefully don't have blood flowing through our body outside the arteries. That's bad. That's bad. So what we're saying is like big R is your radius, so you're going to go from 0 to big R, and then you're going to divide by big R minus 0. I don't think we're going to get much further than this. In fact, I know we're not. The K is a constant. Big R is another constant. Little r is your variable. The We can play around with this more tomorrow. Tonight's homework and the problem set that's due Friday, it's just practice with integration rules. You gotta get yourself to practice. See you guys later.
There you go.